Thanks everyone for coming and thanks for inviting me to speak. I'm going to talk about Quartic Symmetroids and Spectrahedra, and this is the joint work with John Christian Ottem, Kristian Ranestad, and Bernd Sturmfels. And I'll explain most of the words in the title as usual. And this might be a little bit different. So we're going to go into real algebraic geometry, which I think will be a little bit different than what most people here are used to. But if you have any questions, please ask them. We'll start off with a complex thing that's very classical. So a quartic symmetroid is a Cortex Surface in P3, and it's defined as the determinant of a 4x4 matrix of linear form that's symmetric. So you pick your 4 favorite symmetric matrices, you put variables in front of each of them, sum, take the determinant, you get a quartic polynomial, and you look at its the surface it defines in P3. So some fun facts about doing this. First off is that this surface will be nodal, so generically. It will have 10 nodes, as sort of suggested by the picture, there's a node. And if you plug that point into the matrix, you would get a matrix of rank 2. The determinants are singular at lower rank matrices. And I'll talk about this a little bit more. The set of such quartic polynomials has codimension 10 in the space of all quartic polynomials in 4 variables. So these are special quartic polynomials coming this way. And these particular ones were studied by Cayley in a set of memoirs in the 19th century. So in terms of complex algebraic geometry, everything I'm going to tell you today was done in the 19th century. And the interesting things are going to come from trying to look at how this behaves with the real numbers and the eigenvalues of the matrices. But these are the basic objects I want to talk about. Okay. So I want to go to the real numbers. In particular, I'm going to be interested in the case where these symmetric matrices are real, have real entries, and their span contains a positive definite matrix. So just as a reminder, if you have a real symmetric matrix, all of its eigenvalues are real. It's positive definite if all of those eigenvalues are positive. So think identity matrix. Sorry. So, great. I have a couple of reasons for doing this. One reason for doing this is that this intersection, the cone of positive definite matrices with the linear space, is a very nice convex set. It's a convex set that appears in problems of convex optimization, in particular as the feasible set of a semidefinite program. So a polytope is the feasible set of a linear program. A spectrahedron, which is a set like this guy, is the feasible set of the semidefinite program. And so, like algebra, one way to study such a feasible set is to study the polynomial of the surface of that. And I'll talk more about spectrahedra as well. Motivation 2 for doing this is that it's nice. It's a particularly nice thing to do. So these are nice real surfaces, and putting a positive definite matrix, requiring that a positive definite matrix in the span is in this linear space of matrices that you chose, actually puts very nice constraints on your real surface. For example, one of the constraints is that the singularities sort of tell you the rank of the matrix that's involved. And a more relevant constraint is that, for example, so I said over C, this complex surface has 10 nodes, generically. It turns out that if you're going over R, you have a positive definite matrix, then at least one of those has to be real. So you in fact have a real rank 2 matrix somewhere in the span. And that's not true if you sort of review this. So those are Quartic Spectrahedra. I sort of want to back up and talk about this problem more. So this is very specific, right? 4x4 matrices and a 4-dimensional linear space. I want to back up and sort of see the bigger picture of this. And again, if at any point you have questions, ask questions. So let's go more general and look at linear spaces of matrices, of real symmetric matrices. So take your favorite n+1 matrices. And I'm going to look at their span, so I'm going to parameterize their span. And here, J is going to be a D by D symmetric matrix. I'm going to be interested in the polynomial that is its determinant. Will be a real polynomial, homogeneous of degree D. And I want to study these things. And in particular, this defines a convex set. Namely, we have this linear space of real symmetric matrices. It has an intersection. Some of them might be positive, positive semidefinite. And that's a spectrahedron. I'm actually going to productivize that in a moment. But again, so the set of X, so that when you plug them in, this matrix has non-negative eigenvalues, so it's a nice convex set. And since everything is homogeneous, I can, projectivize that. And it turns out when you projectivize, you sort of can no longer say non-negative, but what you can say is that all of the eigenvalues have the same sign. That's sort of well-defined projective. So sort of projective spectrahedron is going to be the set of X in P and R, such that this matrix and the first thing to notice is that this set is bounded by the determinant. Hopefully that's not too bad. So we have this set of matrices where all of the eigenvalues, let's do the non-productive one first. This set of matrices where all of the eigenvalues are positive. We'll move it around, nice open set. And as we go towards the boundary, one of the eigenvalues is going to become negative. It has to go through 0 first. If you have a 0 eigenvalue, the determinant vanishes. So this convex set is bounded by the vanishing of the determinant.
So the complement of the hypersurface, does it have a unique convex component?
That's a good question. So generically, yes. And then you could get special. So for example, if you took a very non-generic, if you took the determinant 0, x1, x2, x3, you get 4 hyperplanes, and then it's, it's not clear when looking at a picture which should be your intersection with the positive origin. All of them are the same. But if you have, maybe the pictures in a moment will make that more, will make the answer more clear. But for sort of generic surfaces, it's clear which component of the complement of the hypersurface should be your positive definite. And again, you should think of these as, feasible regions of an interesting convex optimization. So here's a very tiny little example. Take 2x2 matrices, contain the positive definite matrix at the point x0 equals 1 and x1, x2 equals 0. Nice identity matrix. We have sort of non-projective spectrahedron. We project, we get this guy, and it's bounded by the determinant, which is x0 squared minus x1 squared minus x2 squared. And so, if you want to study these creatures, you can study their bounding polynomials. And in particular, I'm interested in studying both sort of algebraic and topological properties of polynomials coming into play. And that's a sort of broad goal, and then we're going to go back to this very special case that was studied classically. So the first thing is this topological restriction, which is that the polynomials bounding these convex sets are very special. In particular, any polynomial coming this way as a determinant of a linear space that intersects the positive definite cone has a very particular topology. Namely, these polynomials have to be hyperbolic, where what that means is that there's some point, and this point is not unique. So here's a plane curve that comes through. There's some point, and if you take any real line through that point, it intersects the surface in only real points. All of its intersection points with the variety of the polynomial are real. So here's a quartic hyperbolic plane curve. If I pick that point in the middle, and I take any line through that point, I will hit the curve in the blue curve in 4 real points. Spin around the line, it's still true. This is a hyperbolic degree 7 curve. Take the point in the middle, take any real line through it. It will intersect the real plane curve in 7 points, in only real points. So for plane curves, this means that for the real projective plane, you're roughly d over 2 nested ovals, topologically. That's the condition. And then in higher dimensions, things that are basically nested spheres is how we should think of this. An idea of why this is true is this fact that all of the eigenvalues of a real symmetric matrix are real, and that by taking a line, let's imagine that our favorite point was the identity matrix located. Our favorite point was the identity matrix. Let's say that A of P happens to be the identity matrix. That's our favorite point. If I restrict F, parameterize a line through P, that's the determinant of A of P plus A of X. What's the T here? And the roots will give you the reciprocal negative eigenvalues of this matrix. And they all have to be real, because all of the eigenvalues of this real symmetric matrix are real. So that's basically where this comes from, is how you get this restriction. It turns out that for polynomials in just 3 variables, not just a plane curve like the picture, that's the only restriction, is this topological restriction. So if you see a plane curve and it looks like this, it has a determinantal representation with real symmetric matrices that are positive definite in this sort of inner oval. So this was proved by Bill Helton and Victor Vinikoff in 2007. So it's known for, at least 100 years that over C, any plane curve has a symmetric determinantal representation, or a smooth plane curve has a symmetric determinantal representation. And so 100 years later, people get to things that are real and contain these positive definite matrices. So it takes a bit more work, but it's very interesting. And there are no sort of algebraic restrictions. This is a full dimensional, in the set of real polynomials of degree d, this is a full dimensional. You wiggle around the curves and they still have the same topology. And before bumping up the dimension, I want to tell you a nice fact. Some more topological things is if you have a matrix like this and you look at its minors, they're also hyperbolic, have this property uniformity, and they interlace. So if I have, for example, a 4x4 matrix of linear forms, that gives me a nice quartic curve. And if I take, I cross out the last row and the last column, I get a nice 3x3 symmetric matrix. And that gives me a cubic curve. So it turns out that these d minus 1 by d minus 1 minors diagonal, their varieties interlace the variety of your original determinant. This will come up later. And in fact, that is sort of sufficient to show that you have a positive definite matrix. So if I gave you a determinant like this, and you drew the variety of the blue curve, and you took a minor and drew the variety of the red curve, and you saw this picture, you would know secretly that the matrices in here are positive definite. You could also just plug in points and see that the matrices are positive definite. But even if it's a really hard way, this is the way you can do it.
But I mean for each one?
So it turns out that if you have one, you have them all. Okay. So that's dimension 2 spectrahedron. Now I want to increase the dimension of the linear space. So here n was 2. Now we're going to go to n equals 3 and look at things in 3-dimensional ways. So interesting things happen when you take larger dimensions, dimensional linear spaces of matrices. And the reason that you start picking up matrices of lower rank. So in particular, if you look in the space of symmetric matrices and you look at the matrices of rank d minus 2, this has codimension 3. And degree d plus 1 choose 3. So if you take a 3-dimensional projective space of these matrices, you're going to hit it. And you're going to hit it d plus 1 choose 3 times. So generically, over C, if you take a linear space of matrices, you will get d plus 1 choose 3 matrices of rank d minus 2. And in particular, your determinant, you have the surface given by the determinant of the matrix, is going to be, and it's going to be singular at those lower rank matrices. So these are going to turn into nodes on your surface. So here's a determinantal cubic with rank 1 matrices. And so we can try to understand these things. So let's start with cubics. So cubics, if we take 3x3, maybe look at 3x3 matrices, and we try and we go in this setup where we have real symmetric matrices and we intersect the positive definite cone. So 4 plus 1 choose 3. That's not right, is it? Oh yeah, 3. Okay, good. Okay, so 3 plus 1 choose 3, thank God, is 4. So over C you get 4 nodes. And it turns out that if you're in this setup and you have a positive definite matrix in the span of your real matrices, that at least, so an even number of them will be real, generically. So you're either going to have 0, 2, or 4. It turns out that you can't have 0. So you either have 2 or 4 real rank 1 matrices in this span. And the reason you can't have 0 is kind of nice. This yellow spectrahedron in the middle is basically a ball. And if you had only rank 2 matrices, they had a unique kernel. And so you would start to comb hairs on this spectrahedron. So there's sort of nice topological reasons why you have to have a rank 1 matrix. But that's sort of all that can happen. There's two flavors of yellow spectrahedron defined by cubics, by 3 by 3 matrices, generically. Either you have 4 rank 1 matrices, or you have 2 rank 1 matrices. And now we come back to our hero, the Quartic Spectrahedra. So, when we now go to 4 by 4 matrices and look at 3-dimensional spectrahedra, more things happen. So 4 plus 1 choose 3 is 10, so we get 10 matrices. So we intersect and d minus 2 is now 2. So we take a P3 of 4 by 4 symmetric matrices, and we'll find 10 matrices of rank 2 in it, over C. And so now you can start asking lots of questions. So for example, how many of them can be real? And now the real rank 2 matrices will come in 2 flavors. And you can ask how many are of each flavor. The chalk is disappeared. So I'll spend a minute explaining. So if you have a two matrix. Projective, so over real projectively. And the reason is that they have 2 non-zero eigenvalues. That's not too surprising. And again, this is also up to real scaling. So what can you say? You can say that either these 2 non-zero eigenvalues have the same sign, in which case they are semidefinite and lie on the spectrahedron, or they have different signs, in which case they're not. So, same sign. Then they get to be dark blue. Another, if you want to think about this sort of in a more topological way, so we have these 2, I said you have nested spheres now, sort of topologically. On the spectrahedron means that the inner sphere is meeting the outer sphere. Sort of the dark blue bit, the dark blue sphere is meeting the light blue sphere. And off the spectrahedron meaning the light blue sphere is meeting itself. So there are 2 flavors. And if you want to try and sort of understand these real circuits, you can ask, well, what can happen? The answer for qubits was so easy. So it's very tempting to sort of try and figure out what would happen. And how this project actually started was, so Bernd Sturmfels was my advisor in grad school, and like, back when I started grad school years ago, he went around and started asking everyone, what can happen? Show me one with lots and lots of nodes. And eventually he asked the right people, who were Degtyarev and Itenberg, and they answered him. So here's what can happen. This takes a little bit of digesting. And I should say, so I'm only interested in, I'm interested in lessons, but we're only going to look at linear spaces that intersect the rank 2 locus transversely. So no funny, that's sort of generic behavior. So here, okay, you can have alpha blue, dark blue nodes and beta light blue nodes. If and only if both of the numbers are even, and their sum, which is the total number of real nodes on the surface, is between 2 and 10. So here are some examples. Right? Here we have lots of nodes on the surface and 2 nodes off. Here we have no nodes on the spectrahedron and lots of nodes off. 2 nodes on the spectrahedron and no nodes off. And there's more.
But there is always at least one.
But there's always at least one real node somewhere on the surface. And then 2 generically, because real things come in even, or complex things come in even numbers. Yeah. And so they actually did this by studying degenerations of K3 surfaces. And it was fairly abstract, and in particular was very non-constructive and produced examples, and difficult to understand how these constraints come in. So we sort of set about to understand what was going on here. But this is the statement that we're trying to understand. And in order to do that, we looked at some of this classical literature on these types of polynomials. So I said Cayley had this long series of memoirs on these surfaces. And one of the main tools that he used to study them was by picking one of these many nodes that we have and looking at the projection of the surface for the node. So we have surface. This is my only attempt at a drawing. So we have some Cortex surface. We have a node. So this is, use your imaginations. Fun. We want to look at the projection of the surface from a node. So we're taking lines through P, projecting out to P2. The Quartic surface, we have a node. This is going to intersect the rest of the surface in 2 points, generically. So we have a double, this gives a double cover of P2. But it's going to be a branch double cover. So sometimes, we're going to we're only going to have one point, we're going to hit it in a tangent way. And the map branches. And if you took the image of just those points, where it branches in P2, it turns out you get a sextant curve. And normally I find these computations a little bit mysterious, but this one actually makes a lot of sense. So let me convince you that this is a sextant curve. So let's just say, let's move this point to a coordinate point. Then our polynomial has degree 2 in this variable, in this first variable. So it's quadratic in the first variable, and we want to know if you fix the image, the other variables, how many preimages do you have, and when is that number 1 rather than 2? And that's exactly the discriminant of a quadratic polynomial. So I'm writing my polynomial as a polynomial in the other guys times x naught squared plus a polynomial in the other guys times x naught plus a polynomial in the other guys. I want the discriminant of this. And it's exactly the discriminant that everyone knows and loves. And, so if we look at degrees, this A has degree 2, B has degree 3, C has degree 4. So if you take b squared minus 4ac, this is degree 6. And that is the nice sextic branch locus of this map. Branch locus. Branch locus. Okay. And this is the thing that Cayley studied, is this map and this curve. And particularly, he proved something very nice. Someone hands you a nodal Cortex surface, like this yellow guy, and you want to test whether or not it is secretly a symmetroid. It secretly comes as the determinant of a symmetric matrix of linear forms. What you do is you take this branch locus, you take this projection from the node and take the branch locus, and your Cortex surface was a symmetroid, was a determinant, if and only if this sextic curve factors into two cubic curves. That's how you tell. And that's what Cayley showed. So that's a characterization of symmetroids using these branch locus. And, so you took, if you had a symmetroid, you have 10 nodes, you picked one and projected from it, there's 9 other guys. The images of those other guys, under the projection, is exactly the 9 intersections of these two cubic curves. So you have a lot of control. Once you get a handle on that node and you study this projection, you have a lot of control over what's going on with the complex surface. And so what we want to do is study what happens to all of this over R. Any questions before we jump into the real numbers? This is purely like classical complex algebraic geometry. If you ignore the pictures, this is purely complex.
You know how to get the 2 cubics from the original wire?
How do you get the 2 cubics? That will come up later. Well, you have a sextic polynomial factor. You know. I mean, so if you actually wanted to, this is a very testable thing. If you can get your polynomial into this form, you do a change of coordinates, you put your node at this coordinate point, it's fine. Your polynomial will look like this. You take its coefficients, you write down b squared minus 4ac, in poly 2, you say factor. And either 2 cubics come out, which is great, or they don't. And that's one way of getting it. If you actually have the determinant, it turns out that there's better ways. But, does that answer your question? Okay, you'll find more will be said later.
Does every 6 nodal sextic factor?
No. No.
Okay. Nine.
Yeah, I think the answer is no. There are 9 nodal sextics that don't factor 2 cubics. And I think the consequence for these surfaces is that there are 10 nodal quartics that are not symmetroids. Okay. So now let's jump into the real numbers. So here's what happens to these projections over the real numbers. And you have 2 different flavors of nodes, you have 2 different flavors of projection. The first flavor of projection, you pick a point, you pick a dark blue point on the region and you project from it. And it turns out what happens is that you don't really have any real ramification. Is that if you do this, then your sextic polynomial is non-negative. It factors as 2 cubics, but they're complex conjugates of each other. So this was, I'm calling these B1 and B2. So you project from a dark blue point, and these 2 cubics are complex. And then in fact what happens is sort of, this is the picture that you see. In fact, if you're right up at the node, all you see is the tangent column. That's the image of the dark blue spectrahedron, and then the surface is everything else. A was you sort of see a conic if you're looking at the spectrahedron sitting from the dark blue node. And that's not so interesting. What's more interesting is if you project from a node far away, one of these rank 2 matrices with 2 different signs of eigenvalues. And then what happens is that your 2 branch cubics are both real and hyperbolic, so they have an oval. Cubics that look like that. And in fact, so there's a green oval and a red oval, and their intersection is the image of this spectrahedron through this projection.
Intersection of the ovals.
Yeah, so you have a red cubic and a green cubic, red cubic branch and a green cubic branch, and they have ovals. Sort of, they bound disky things and intersect. So this would be the image of the spectrahedron under this projection. And that turns out to be the sort of real and spectrahedral analog of Cayley's statement. And this maybe gets back to Morgan's question a little bit. So now, here's a small idea of why that happens. So if we start making assumptions again, if we put our node, we had a node, we put it at a coordinate point because that's convenient. And if we happen to take a very special rank 2 matrix to be sitting at that point, which turns out not actually to be that special, but if we pick this very special rank 2 matrix to be A of P, to be the matrix that's right there, then what happens is that these branch cubics are exactly diagonal minors of the rest of the matrix. So you took, this is a matrix in linear forms in x1, x2, x3. It's what the mystery colored box is. And if you took the determinant of this whole thing to get the surface, and you took the branch locus of projection from this point, you get 2 cubics, and those 2 cubics would be diagonal minors of this matrix as well. And they have to, and this has, we said this contains a positive definite matrix, so we know that they're hyperbolic. And in fact, you get some interlacing properties of these 2 guys and this degree 2 conic in the middle. And so what happens is you have 1 red cubic branch, 1 green cubic branch, and this little 2 by 2 matrix, the conic one, the 2 by 2 matrix interlaces both of them. So you have a lot of control over it. And Morgan, this might be a better way of getting the 2 cubics involved in the branch filter. But so you have a lot of control over the real picture. And in particular, we know what the spectrahedron looks like, and we know what the projections of the spectrahedral nodes look like. And this at least helps explain this even number phenomenon that happens, is that if you have, so the spectrahedral nodes get projected to intersections of these cubics on the intersection of the spectrahedron, and these are intersections of 2 ovals. And so in particular, ovals have to intersect an even number of times. And so there have to be an even number. So there have to be an even number of intersections of these 2 ovals down here, and what that means is there have to be an even number, they come from an even number of spectrahedral nodes on the surface upstairs. And so this is sort of a very concrete way of seeing why there has to be this split of even things, even range 2 nodes of one flavor and of another flavor through this very sort of complex system.
The spectrahedron node not map into game theory or
no, because they map into the intersection of the cubics. And the cubics are sort of spectrahedral themselves. Like this is a convex. Each of the cubic ovals are convex. You have 2 convex ovals. You can get one. Convex, but not, you can, convex things can intersect in lots of things. Most of the pictures have not that many nodes because it starts getting a bit like, actually no, this one had like, it's hard to see, but there's 6 maybe. Had to work really hard to get a picture that are also spread out. But yeah, so you can get, well, according to this theorem, you can get not all 10. So you can get 8. And you have a very messy picture that I probably don't want to show. So. Yeah, so they can intersect quite a lot. So we're very pleased that this is a sort of concrete way of seeing part of this theorem of Degtyarev and Itenberg. And then the question is, well, you have all these restrictions on what sorts of surfaces can show up. Do they actually show up? And so to understand whether or not you get all of these different types, we just found them and found a bunch of matrices. So there's 20 types of Quartic Spectrahedra. These numbers are not particularly interesting. But if you want a Cortex Surface with 2 spectrahedral nodes and I think 2 nodes total, you use these 4 matrices and take the determinant and keep going. There's a lot of them. So they can be found. They exist, and with small numbers. And the pictures are, of course, so you get lots of, here's one of the elusive, guys with 10 nodes all on the spectrahedron. Here's one with none, and you get all of these many different flavors. And so that's sort of what can happen with these. Of course, there's lots of non-generic things. So this was all a generic picture. You intersect them into locus transversely. There's lots of beautiful non-generic things that can happen. For example, you might intersect the rank 2 locus in a curve of rank 2. You might just intersect it too much. And then you get, here you intersect it in 2 circles. You might contain rank 1 matrices. So you can intersect with rank 2 locus in a lot of non-generic ways that you sort of don't worry about too much. So there's still a lot of things, even for this very small case, there's still a lot of things that are unknown. And so maybe, and of course this was only degree 4 things. So it gets a little bit harder. This is a degree 7 symmetroidal surface. So maybe I'll conclude and just say that sort of the study of spectrahedra and symmetroids and determinantal surfaces is beautiful and classical and involves things from a lot of different areas of mathematics. And in particular, there's still a lot of things that are open and unknown about them. Certainly algebraic geometry is part of the solution to that. With that, I will leave your attention.
Questions?
Okay, so what is it actually that you want to know about this thing?
Well, lots of, so, understanding where the nodes are is very interesting. And then for when you go to larger dimensions, then you intersect all sorts of stuff, right? If you start bumping up. So understanding the singularities is very interesting. And these examples are still very small from a practical, people who do semidefinite programming do like enormous things, but.
Yeah, so what do they want to understand about them? Okay.
Well, so for example, when you optimize over these dark blue spectrahedron, one thing you might want to do is hit a low rank matrix. That's like good news from an optimization standpoint. That's where a lot of like low rank recovery, that's a lot of this comes this way. So those are the good solutions with the singular solution. So understanding where they are would be very nice. And again, this is sort of too small to people who do, if you can draw them, then you don't need so much. But understanding the behavior of the low rank things is very interesting.
Before do you have Torelli style interpretation lattice?
Yeah, so that's how Degtyarev and Itenberg did there. So I think this is true that if you take if you had done a smooth sextic curve down here, then your quartic would have been a K3 surface. And they sort of use the generations of this to get these. That's how they study that.
Model Quartic is still using surfaces.
Yeah, that's what they do. So yeah, there's certainly all of that structure. We were trying to avoid all of that structure. Because we wanted to see them in construction.
I mean, but I mean, are there any positives with the Quintic? I mean, so we know that the most for K3, we understand everything. This will be able to keep that and stuff like that. But as soon as you go to Quintic and stuff like that, it's much more difficult.
That was one of the other motivations, was to do something that might possibly be extended. And yeah, I don't know. If anyone can tell me about quintics, please do.
But also you have a spectrahedron story for K3 using X8.
Spectrahedral. I mean, I can give you a spectrahedral story. If you give me a determinant, I can give you a spectrahedral story. But I don't know. Yeah, I don't know.
What question is there a spectrahedron any higher degree? With the maximum number of nodes, like we're all the nodes are real non-spectrahedron. That's very fucking screen.
So you can certainly ask the same question, where you have even, for quintics, 5 plus 1 choose 3 nodes of rank 3, can you think them all on this definition? Yeah, I don't know the answer.